I'll recap how we got here and then pick up where we left off. So we started with a derivative relationship, rearranged that into two integrals. One integral equals another integral. Put in our integrand, substituted in our integrand, chose our upper and lower limits of integration, depending on whether we wanted to find a particular area delta x or we wanted to find the function x of t. Then we determined the antiderivatives of the integrands on either side. And I notice I made a mistake here. I left out the t to the fourth right there. So we've got our antiderivative of the velocity function with respect to time and the antiderivative of that little 1 there with respect to x. So that's where we are now. Got our antiderivatives. And it's time to apply the second fundamental theorem of calculus, which we had written down like this. If we have some function f of x integrated from x1 to x2, then the result of that is the antiderivative of that function evaluated at the final value of our independent variable x2 minus the antiderivative of that function evaluated at the initial value of our independent variable x1. So applying that, again, we'll do our two options. So start with option 1, where we're trying to find a specific area delta x. Let's put some numerical values to that. Let's say we want to find the displacement delta x for an object between times t1 equals 1 second and t2 equals 3 seconds. We want to find this specific displacement. Okay, so integrate dx from x1 to x2. And time is now going from 1 second, we put in our lower limit, to 3 seconds, our upper limit. So state those upper and lower limits. And now the fundamental theorem of calculus takes us to our next step. What we do is replace our definite integral with the antiderivative of the integrand with respect to the independent variable. So the antiderivative is x plus c. We put that in brackets and then rewrite our lower and upper limits on the lower right hand and upper right hand corners of those brackets, indicating that we're going to evaluate this antiderivative at the final value, x2, and then subtract from that our antiderivative evaluated at the initial value, x1. Over on this side, we've replaced our definite integral with the antiderivative we determined from our antiderivative rule for polynomials. So here's that antiderivative, and we're going to evaluate it at 3 seconds, and then subtract from that the antiderivative evaluated at 1 second. So written out, that looks like this long line. So left-hand side, this will be x2 going in for x, so x2 plus c minus x1 going in for x, x1 plus c. And you'll note how c minus c, we don't know what that constant is, that constant term that we had to add when finding the antiderivative, but it's not going to matter. C minus c cancels out. We don't need to worry about it. How nice. Then, on the right-hand side, 3 seconds is going in for t, for everywhere t is, there, and there. So that's our antiderivative evaluated at t equals 3 seconds. And then minus that same antiderivative evaluated at 1 second. So 1 second will go in for t everywhere. So here's our polynomial, antiderivative polynomial with t equals 1 second, 1 second, 1 second. On this side, there's an unknown constant term, c prime. We don't know what that constant is, but we can see that c prime minus c prime is going to cancel. How nice. We don't need to know what that constant term is if all we want to find is this specific displacement between this fixed lower and upper limit. Okay, looking at our right-hand side here, we've just got a bunch of numbers to crunch. Left-hand side, just all that's left is x2 minus x1. So there we have it. x2 minus x1 equals, crunch all these numbers, we get 98 meters. That is the area under that curve between time 1 and time 2. So 98 meters would be the value of this area here between these two times. So that's the displacement of our object between those two times. That was option 1. Now, option 2. Here what we want to find is the function x of t. So not some specific displacement, but since we know velocity is a function of time, we want to find position as a function of time. Now we're aware that we need some extra piece of information. We're aware that, let's see, going back to this earlier document, if we have some velocity versus time function, the one piece of information we can't get, the missing piece of information, is your starting position or some particular position. We cannot determine position from the velocity function alone. You have to be told that extra piece of info. And right here is where that happens. If we want to find our position function, we need to be told the position at some specific time. So here's our extra info. We'll say that at 1 second, the object is located at 7 meters. If we're told that, then we can actually find our position function. That's the missing info that wasn't in our velocity graph. All right. So here now for our limits, we'll say that at time 1 second, our starting time, the position x naught will be 7 meters. So the lower limit for time 1 second, the lower limit for x, 7 meters. So it's at this location at this time. The lower limits have to match. Now our upper limit is just going to be some floating time t that will allow to be a variable. So t will have some future value t when x has some future value x of t. And so there is our x of t function that we're trying to find. All right, apply the fundamental theorem of calculus and replace each definite integral with the antiderivative of its integrand evaluated at the final position and the initial position. So this 1 times x here becomes x plus c, evaluated at x of t and 7 meters. And here the antiderivative of our velocity function with respect to time, that's this, gets evaluated at 1 second and at t. So on the left-hand side, we're going to plug x of t in for x. So this becomes x of t plus c minus the 7 meters plugged in for x, 7 plus c. As before, c and c cancel out. We don't need to know that constant. On the right-hand side, we're going to put t in for t, t, and t. So there is our polynomial in terms of some variable floating future time t. And then we'll subtract from that our antiderivative evaluated at the starting time, 1 second. So we'll put in 1 second for t, t, and t. So that's this here. C prime, whatever that constant is, cancels with C prime, whatever that constant is. We don't need to worry about it. And so, in fact, since we've seen that whether we're going with option A or B here, the constants always cancel out, we actually tend to be lazy and just not write those constant terms in at all. We generally leave them out because we know they're going to immediately cancel. Simplifying here, the left-hand side becomes x minus 7. The right-hand side, let's see. Oh, no changes on the right-hand side yet. Left-hand side became x minus 7. And then we're just going to simplify. So since what we really want to know is x of t, this minus 7 meters, I'm going to add that to both sides. So add 7 to both sides. So effectively we move that 7 meters over. Simplify all these here, c prime, cancel with c prime. So do the arithmetic, crunch those, add the 7 meters over, and we get this as our final answer here. That's what we wanted. The position as a function of time. There's this constant term on there, the 3.75 that came from simplifying all of this. And we were only able to know the value of that constant term because we added in this missing information up here. Here was that key missing info that allowed us to determine that constant that disappears when we take the derivative of our position function. Okay, so I want to conclude by pointing out, of all of these steps, which we've gone through in very careful detail here, of all of these steps, what do you actually need to show on your page to demonstrate your understanding? So what actually needs to be on the page when you're showing your work? All right, here's a clean copy of the first page. So let me go through the minimum things you need to have on your page. 1, you start by stating the derivative relationship you're working with. This is you stating your equation. That's your starting point. That should be on your page. The next thing that has to be on your page is either this line or this line, depending on whether you're doing option A or option B. So the next thing that should be on your page is you showing that you've rearranged this derivative into two integrals, a left-hand side integral and a right-hand side integral, with your upper and lower limits indicated. You have to show those upper and lower limits because those define what it is that you're doing. Those define whether you're finding a fixed area or whether you're trying to find some function. So those have to be shown and they have to match up. Okay, so next thing that needs to be on your page is this line. Then I'd say after that, you don't need to show separately these antiderivatives. I'd say the next thing that could be on your page would be this line or this line, depending on where you're doing option A or B. So after showing your two integrals with your limits, and actually you should have the numerical values plugged in for the limits if you're using numerical values, like let's say here where I've got the 1 second, the 3 seconds, you should have those plugged in. That you should show the numerical values. Likewise down here, you should show the 1 second and the 7 meters. Specify those values to show that. And then you're indicating this step where you've got the antiderivative in brackets on either side with the lower and upper limits on the right-hand corners of your bracket. As I said earlier, the little constant c, we know it's going to cancel out right away, so typically we're lazy and we don't even bother to write the little constant c there. Okay, and then your final thing you should have would be the result of, I guess not the final thing. Next you'll want to show would be, say, this, where you're showing your substitutions and your simplification of the right hand and of the left hand side. So there's your final answer. Or if you're doing this method, you should show your substitutions, how you're plugging in the upper and lower limits, and then state your final answer. You express those steps on the page and it'll be very clear to the reader that you know what you're doing.